Well, I think that our speaker today actually needs very little introduction. We're so honored to have him as our presenter today. As probably many of you know, he's President and Chief Technology Officer on the Board of Directors for the Warner-Babcock Institute for Green Chemistry. He's perhaps better known for being the co-author of the text Green Chemistry in Practice with Paul and Astis. Paul are considered the fathers of green chemistry, and he has published over 200 patents, papers, and books. But I'm really not going to spend a lot of with his introduction. You can find all of the details you can find on our website. To turn it over to John, and take it away, John.
Great. Thank you very much, Lynn. Thank you, Clinton. I'm very happy to be asked to give this talk today. It's my pleasure. It's very strange for me. I'm used to speaking to people and seeing their faces and things like that, and modify my talk by, if someone's head is starting to hit the ground, I change what I'm saying to try to get them back awake. Here in a completely disembodied function, it's something new to me, but I'll do the best that I can. I wanted to give this talk in a different kind of way and go through some observations, some comments, and now after being at this for, oh man, over 20 years now, I've kind of picked up some interesting observations, and so I wanted to run it by all of you. And so some of these slides you've seen before. A lot of them are brand new. This will be the first time that I'm presenting some of this information ever, so I welcome the feedback either immediately or over time, as we go forward. But I want to start by just a bunch of observations. And one of the observations that I've come to realize is that our society, for whatever reason, pays more attention to identifying and describing a problem than solving a problem. What do I mean by that? It's kind of interesting. I've been a chemist for over 32 years. I'm getting old. And over my career, I've published well over 200 papers and patents and abstracts of talks and various things like that. And, I've probably in my life invented a couple dozen technologies that arguably have replaced hazardous things with real-world solutions to those problems that actually remove that hazard from that application. And, I don't know that many people on the phone know any of those inventions. It's a strange thing. However, a couple years ago, I was interviewed by a magazine, and I made a casual mention of bisphenol A being in cash register receipts. And for the next 6 months, oh my God, 6 countries called me, governments, 5 television shows, 20 radio shows, infinite number of magazines and things. It was interesting that I suggested that BPA was a problem because it was in cash register receipts. And throughout my career, I got far more attention because of that single statement than all the things that I did to invent the alternative. And I find that kind of interesting. In fact, I was even in Woman's World magazine in February on the same page as a cat pushing a shopping carriage, which it talks about John Warner identifying BPA and cash register receipts. Now, this is important. People need to know the problems that they're facing. But I think we need to step back and ask ourselves, are we spending an equal amount, or at least an appropriate amount of time, trying to identify the solutions to the problems as we are trying to identify the problems themselves? A second observation that I've made that's kind of interesting is that many people have an all-or-nothing mentality when it comes to sustainability. What I mean by that, this manifests itself in many ways, but in the science community, I'm actually going to show you guys a slide of, Robert Burns Woodward is a Nobel laureate in chemistry, is, in my opinion, the most famous organic chemist that ever lived. And here I have a slide that shows the multiple step synthesis of a famous molecule called reserpine. If we were to go, all of us were to go to a science seminar, some technical talk where some person has been working on this synthesis, and they give a brilliant presentation of this synthesis. And then after the talk, people will ask questions like, ooh, what was the regiospecificity of this reaction here? Or perhaps did you see any rearranged product at this point? Or what was the effect of pH on this reaction? And every question will be probing the scientific methodology used. Now, if that person gave exactly the same talk, but at 1 second in their presentation just made side mention, I used water instead of dichloromethane in this step, and then everything else was identical. Ironically, every question afterwards would be, well, isn't this toxic? Isn't this toxic? Isn't this hazardous? If the person mentions sustainability, every question is, why didn't you do this? Why didn't you do this? They get a pass if they don't mention it, but if they mention it just a little, we beat them up because they didn't do enough. And I think we need to step back and think a little bit about that observation, that science doesn't work that way. Very rarely are there all or nothings, and just kind of explore that reaction that we have to people that are trying to do a little bit, and then it's almost better that they say nothing than they say a little. And so it's just another observation. Now again, let me quick give a background of green chemistry. I want to make first an initial disclaimer that I am not so presumptuous to say that anything that I think anyone else needs subscribe to. That my attitude is that I've been on this earth for 50 years. I've developed my way of looking at the world that works for me. I am happy to share that as my perspective, but no way am I saying anyone else needs to subscribe to the way I look at the world. So as I give this presentation and I give my thoughts, please make sure that you understand I'm not so presumptuous to believe I have all the answers. It works for me. And if anything I have to say helps anyone else put things in perspective, great. But I'm not preaching that this is the way it must be. This is just what works for me. Now, you guys know that, Paul Anastas and I, we wrote the book on green chemistry now quite a few years ago, and that the technical definition, green chemistry, the design of chemical products and processes that reduce or eliminate the use or generation of hazardous substances. Two things I have on blue in this slide is design and use and or generation. I think that those are key because the whole point of green chemistry is to design materials that are safe, environmentally benign, and non-toxic. It's not so much an evaluation of products and services. The whole intent was to get at the design stage of a process. And then the second thing is use and or generation, meaning it's not just about the end product. This isn't just a measure of the sustainability, toxicity, whatever environmental impact that a product has at when the consumer is touching it, but green chemistry seeks to look at the entire life cycle and go back, how is it manufactured and everything like that. So those two things I want to highlight as being kind of critical. And of course, this, Paul and I were, I think equally stunned at, how the world reacted to this book. We did not, when we wrote this book, think that, it would make as much of a hit as it did. Well, obviously we're pleased, but these two kids from Quincy write this book. It gets translated into, I think it's now 15 different languages. In my opinion, what differentiates green chemistry from other methodologies that are equally important and equally valid for different purposes is that the 12 principles of green chemistry, in my opinion, are kind of like a checklist that speaks to the designer, the chemical or materials designer, to essentially what they can do to address these issues. Okay, and so it's not really a government policy program. It's not really, something that's more aspirational. This is the intent, in my opinion, is to be able to actually affect change. You measure, one can measure sustainability in any way that they want, but if they want to improve the sustainability performance, they use the 12 principles, and I'll come back to that thought in a minute. But what I have to make a very important understanding is that in no way do I feel that green chemistry is a birth of ethics in chemistry. Okay, it isn't as if people doing chemistry that have been working in the chemical industry before green chemistry were somehow absent of an ethical compulsion. It is my assumption that people have always cared deeply about human health, the environment, they love their children, they want the world to be a better place. Green chemistry is not introducing this kind of ethic to chemistry. I strongly believe that the people that were being chemists long before green chemistry came on board cared. But where there's a difference is in the approach. What I mean by that is that I feel that when I went to school as a chemist, it was well known that chemistry was dangerous, and it was assumed it had to be. There was no question that green chemistry had to be dangerous, but that you accepted that risk because you were making drugs to cure sick people, you were making new materials to do amazing things, and agricultural agents to feed the sick, and so we took it as a sacrifice upon ourselves to work with toxic materials because of the better good that it's doing. But it was okay because we would wear gloves to protect our skin, we'd wear masks to protect our lungs, we'd wear goggles to protect our eyes, we'd install scrubbers and smokestacks to protect the air, the land, and the sea. That's how we could get away with working with nasty things, because we would protect the outside world by mitigating exposure. Now, obviously, this works to a certain extent, and there's been Herculean efforts to develop even better technologies to protect people. But if you think about it, every time a disaster has happened, every time something bad has happened where human health or the environment has been put in peril, it wasn't as if these technologies were absent. They failed. A glove developed a pinhole, a mask failed, the scrubber in a smokestack stopped working, other things happened. We are dependent on these technologies for the future, but if green chemistry is seen as a revolution changing, this is where it's changing the mindset, because what it's doing is it's saying we're mitigating risk not through exposure control, but in fact doing it through the intrinsic hazard in the first place. And if there's one central idea that is green chemistry, it is this. It is that when one designs a molecule, if I want to make a red pigment for a textile, I know what color red I need to make it. I know that I want it to stick to the fabric. I know that I don't want it to oxidize in the air. I know that I don't want it to fade. Actually, what I also want to do is make sure it's not a carcinogen, it's not toxic, and there's no environmental negatives. That is the part that is green chemistry, is to add to the criteria those things as part of the design. So it's not as if people weren't doing it already, but it was done in a more haphazard way. Whereas what green chemistry is saying, let's create the criteria to do this in the same way that we would measure the color of a molecule or would measure how to make it stick to a fabric or anything else. How do we measure how to make something that is environmentally benign and non-toxic in the first place? So the mindset was back in the early 90s when the Pollution Prevention Act was happening, is that, you know, we looked at it and said, people don't talk about making things environmentally benign. God knows that scientists love to have conferences. Every day there are hundreds and hundreds of conferences across the world on all kinds of different topics. Back in the early 90s, there was no science called green chemistry, and so there was no way for scientists to talk about their advances in making things that are less carcinogenic or making things that are less, you know, neurotoxic or use less energy or be more biodegradable or whatnot. There was no mechanism to communicate that advance, and so it was really just a bunch of random happenstances. And so the green chemistry was designed to create a science. So there could be journals called green chemistry. So there could be conferences called green chemistry. So there could be webinars in the Great Lakes about green chemistry to attract the scientific population to share ideas and grow. That's how you solve problems, if you get people of common cause to be sharing it as a science. So the 12 principles of green chemistry were designed to create that. So it wasn't that people didn't care about it already. It was that this moved it from some nebulous, gee, we should really kind of do this, to this is how you do it. Let's create a science around it, and let's do it from that perspective. So that's the point. And now, of course, you know, anyone who's heard me talk understands that I have, you know, very, very strong, you know, opinions about our education system, because, of course, we aren't currently training chemists to understand these issues. You know, you know, in 2008, this is the latest data that I could find, we graduated just in the United States, not worldwide, just in the United States, nearly over 18,000 undergraduate degrees in chemistry and chemical engineering, over 3,000 master's degrees, and over 3,000 doctoral degrees in chemistry. I like this statistic because I think it's important. In 2004 was the first time more women became chemists than men. All right, and so right now we have this thing in which we really need to be teaching what are the implications of chemicals on reproductive health, on human health, on environmental health, and yet right now, to get a degree in chemistry, still today, I've been at this for a long time, there are no chemistry programs in the country, and there's some things happening in other countries that might qualify, but certainly in the United States, there are still no universities that require students who are going to go out and practice chemistry in the outside world to have any knowledge of toxicity and environmental impact. And so I feel that really to move this ball forward, it isn't just about looking at products and saying to industry, you should make safe products. I really think that to really make a change, to really change the world and move us on a sustainable pathway, we got to look at how do we train scientists and what tools do we give them so when they get into industry, they're capable of solving these problems. Okay, and so that's the way that I look at this, and so I feel that as important as it is to be working with industry to create sustainable technologies, it's also really important to look at how we manufacture, if you will, chemists in the first place. Okay, and so, I love the American Chemical Society. I've been a lifelong member. The moment I became a chemistry major as an undergraduate, I joined, and I've been a member ever since. They do amazing things. The field of chemistry, its journals, its conferences, everything that the ACS does is really amazing. But just because something is excellent doesn't mean it couldn't be better. I feel that the ACS is still not quite up to speed with the moral and ethical component and the global competitiveness component that is necessary to introduce these concepts to the chemistry curriculum. Right now the ACS has these guidelines. They're not mandatory. Universities don't have to use these guidelines. It's really voluntary. But they provide guidelines that if you're giving a degree in chemistry, you should have calculus, you should have biochemistry, you have instrumentation, independent work. Still in 2012, there's really no emphasis in toxicology, environmental impact, sustainability, law and policy. They're trying. I do believe that this next round, I have all my hopes and dreams that ACS is gonna have the next round do it. Right now, all they do is they preach to the choir. If a student is interested, well, a department should do what they can to help them. But I feel that this isn't those that are interested. I think that there is an imperative that anyone who is going to go out and make a new molecule be given the tools to assess whether what they're about to make is potentially the most toxic neurotoxin in history or carcinogen or not. And until we address how we teach scientists, we've still got a long way to go. I'll get off that soapbox now. With some of my students back when I was a professor, and I continue at the Institute with Beyond Benign, we do publish a lot. Way back in, we've been at this for almost a decade now, that, Nick Anastas, Paul Anastas' brother, and I have actually published papers on how do you design products, what is a logical flow of how you identify and design molecules that are non-toxic, okay? And so there are papers that one can find that give these kinds of flow charts that we've been working on. This is part of that academic structure. But the other thing is the EPA right now has websites and tools that one can log on to and assess the potential toxicity of molecules. Most universities graduate students having never even heard of those freely available tools. So it's not the sophisticated fine-tuning. I'm talking just big picture general stuff. And next month, Amy Cannon, the executive director of Beyond Benign, will be speaking specifically on this subject. So I'll get off my soapbox now and move on. Okay, so we all have jobs to do in sustainability, and in no way will I ever suggest that green chemistry is more important or less important. We all have our roles to play. And so sometimes people, I think legitimately say, oh, how does green chemistry fit in with like alternatives assessment? And I actually think they're critically linked together, and this is a hand-in-hand. We've got to work together, and this is the way that I look at it. Is, you know, if you think of all the products and processes, everything that's available to society from a chemicals and material science perspective, I would argue that if we do an assessment and we try to evaluate the toxicity, environmental impact, sustainability, whatever metric we want to, probably 10% or less will pass muster in everyone's eyes. 90% of the things that we're doing out there have problems. They might, you know, have a toxic intermediate. They might be persistent in the environment. They might be non-biodegradable. Who knows, you know, what might be going on. Too much energy in the manufacturing. We have a long way to go. Now, if people do an alternatives assessment and seek what is the best opportunities that are out there right now so that you just change in your supply chain and you get a better material, it is my belief that you're going to win 25% of the time. At best, that's the best that we can do, is that there are 25% of the time we can find something better to improve the lot. But in my estimation, there's at least 65% or more haven't been invented yet. This isn't people making choices because they just choose to not make the change. It is my wholehearted belief, you know, being at this for so long, that the alternatives don't exist. And so it's not picking and choosing down the supply chain for a better thing. It's really, how do we get people to invent them in the first place? And if education isn't teaching the students how to do it, well, how do we get from point A to point B? And so that's the way that I look at the whole role of you know, the difference between alternatives assessment and green chemistry. Now, what I'm saying, though, is when green chemistry invents a new alternative, we got to rely on alternatives assessment to make sure we're playing in the right game. And so alternative assessment steers green chemistry into what to invent, because they're identifying the needs, and then they're keeping us honest afterward, because once we do invent, we're going to make sure that we are, in fact, more sustainable than we were. So it's not an either-or situation. We need to be working hand in hand, but we've got to recognize what happens when an alternative assessment falls short and fails to identify a better alternative. Right now, if the chemist and the designers aren't at the table inventing, we just use the bad. And so going forward, this is what we need to do. Now, the chemical enterprises, in my opinion, have been around for over 150 years. Lavoisier, back in the 1800s, you know, arguably one of the founders of the field of chemistry and material science. It's been around for a long time. Okay, we have all of our products, all our goods and services. Everything has been evolved over a century and a half. Now, green chemistry has just come on the scene very recently. There's no magic switch that we can throw, and tomorrow everything instantly become green. This is going to take decades and decades of figuring out how to make a molecule that, you know, is non-toxic in this environment, how to make a molecule that's not going to be persistent in the environment, how to make a molecule to do all these different things. And so if we're going to want these 65% other materials to be invented, we have to realize that we're going to have to be patient. We can't insist on it immediately, because then it's not going to happen that way. That's not the way science grows. And so that's the way I look at that. And it's important to really kind of put it in the perspective of, where do products come from? If you think about it, molecules, you know, we turn them into materials, and then we call that basic research. Then we take materials and we turn them into components. We call that applied research. We turn components into devices. We call that development. And then we make a bunch of them, and we call that manufacturing. Now, obviously, this whole process has got the environment in dead center, right? Where do those molecules come from in the first place? And after the product is done, where does it go at the end of its life? Well, obviously, all of these interactions with the environment is what we're talking about. Now, there are important roles for everyone in this process to play. I would argue that smart manufacturers are already caring about the environment, smart people that are building market cases. There's a lot going on historically for the last several decades to try to think this through. But I feel, in my opinion, that places where changes must happen is here where the chemists play. And in fact, like I said, that's kind of new on the scene. No college, no university is training chemists to understand the environmental implications of basic research and applied research. So all we can do is rely on alternative assessment right now, because those are the only people that are trying. Until we change the game here in basic and applied research, we're stuck with what we're stuck. That's the imperative, is how do we get in and train the future chemists and the existing chemists. Next question is about chemicals and green chemistry and how it relates to chemicals policy. Okay, now this is something that has often people have misunderstood. Let me make a disclaimer right now. We urgently need excellent chemicals policy. Chemicals policy protects human health and the environment, and the people who are working in chemicals policy are literally heroically doing important work. Green chemistry is not a replacement for that work. Let me say that a second time. Green chemistry is not a replacement for that work. The problem, as I see it, is chemicals policy works on the demand side, and they can do an excellent job at creating the demand, but if we don't have chemists inventing the alternatives, we're kind of stuck at an impasse. And so I don't believe green chemistry can be, as effective as possible without good chemicals policy. I'm not so naive to believe it's just going to spontaneously happen. So chemicals policy is still an important part of our future and forever. And so green chemistry isn't to displace chemicals policy, it's to work with it. But all the demand in the world, if we don't have the skill set to invent the alternatives, the demand just simply, in my opinion, isn't enough. And so we need both, not one or the other. We need both. And so that's how, in my opinion, green chemistry fits with chemicals policy, if they go hand in hand. How about the bigger picture of sustainability? This is another really, frustrating thing. I'll editorialize in a second. But first of all, the disclaimer, this is the way I look at the world. I am not presumptuous enough to believe that anyone listening to me right now need adopt what I'm about to say. It works for me. And the way I look at this is I see sustainability as an overarching concept that touches every aspect of human existence. We could talk about sustainable economics, or agriculture, or education, or business, or chemistry, or engineering. We could slice this pie up in millions of different ways. Sustainability touches all aspects. If we look at the part that deals with chemistry and materials, we call that sustainable chemistry. Okay? And in sustainable chemistry, we could talk about chemicals policy. We could talk about remediation technologies. We could talk about exposure controls. We could talk about green chemistry as a subset of sustainable chemistry, water purification, alternative energy, all kinds of others. On the EPA website, it says in glaring letters, green chemistry, also known as sustainable chemistry. They have an absolute right to their opinion. I don't agree. I feel that sustainable chemistry and green chemistry are not synonymous, that there's a big difference. Green chemistry is an overarching principle that talks about policy. If you have a hazardous material and you develop better exposure controls, there is an aspect of that that touches sustainability. We need water purification technologies. That is a sustainable chemistry. We need alternative energies. That is a sustainable chemistry technology. But if I make a solar panel with toxic materials, we need it. Okay, sustainable energy is a requirement. We haven't finished our job yet, though. Is that truly sustainable if it's using toxic materials? In 20 years, when we unbolt it and put it in a landfill, what happens to those toxic materials? So I'm not suggesting we don't develop alternative energy. We need it. It's desperate. But then it is a sustainable technology, sustainable chemistry. But what green chemistry is it's actually application agnostic, in my opinion. There is no such thing as a green chemistry technology. Green chemistry is a mechanism that goes into everything. And so the building blocks that make a solar energy panel, if they're done with minimal impact on human health and the environment, that's where green chemistry plays. If you make a water purification device and the molecules that go into making that water filtration device are toxic, if you make them less toxic, that's green chemistry. If you make a pharmaceutical, that the manufacturing process is less toxic or it has less environmental impact. So essentially what green chemistry is saying is the building blocks, the solvents, the catalysts, the renewable feedstocks, the toxicity, the persistence, the energy use. You know, obviously I have a bias. I would look at this in 12 different ways and look at it as the 12 principles of green chemistry. This is how I look at how green chemistry is a subset of sustainable chemistry, which is a subset of the big picture sustainability. And in no way do I think green chemistry is any more important than anything else that people are doing. The only difference with green chemistry is that is the thing that chemists can do to participate in this very important structure. But it doesn't mean that it's the only thing that needs to be done. There are a lot of other things that need to be done. Green chemistry fits as a piece into a many-piece puzzle. So that's the way that I look at it. I try to be completely non-presumptuous. It doesn't do everything. We need a lot more than just green chemistry. But if you're a chemist working in a lab, green chemistry is the way that you participate in sustainability. That's my view on that. All right, so the other thing I want to talk about is green chemistry wasn't originally designed as an assessment tool. It can be used as such, but it really was designed as a design tool. Okay, and what I mean, I use golf as a metaphor for this. I am a horrible golfer. My wife, Amy, is an amazing golfer, so I can use this analogy because I've watched her golf. If you got a bunch of golfers together and you wanted to assess their game, you could set them up and you could have them, how far can they drive, how straight does the golfer hit, how accurate is the short game, how do they get out of traps, how consistent, and you could set up an Excel spreadsheet to measure those golfers. So if you had 5 golfers, you filled out an Excel spreadsheet, you could say on this course, this golfer's going to win, this golfer's going to come in second. These are measurable attributes, and they're very important to understand how good a golfer is. But what if you want to do better? What if you want to improve? Does knowing these numbers do anything to make you better? It's important. It's critical. No way do I think it's not a critical part of the puzzle, but it doesn't help you make it better. You know, my wife has screamed at me, drive straighter, and I don't. You know, knowing that I drive bad doesn't make me any better. Where what you have to do if you want to improve the golf game is you go to the intangibles. How does the golfer grip the club? How does the golfer hold their shoulders? How do they place their feet? How do they swing the club? You know, all those kinds of things there. Those are the adjustable components that are a little less easy to measure and to put on an Excel spreadsheet, but critical to improve the performance from a sustainability perspective. So that's how green chemistry fits into that perspective. We need the assessment tools. They are critical. We have to continue to improve them, and people should use them. But if we want to improve and make that assessment tool come out better tomorrow, green chemistry is the mechanism that helps us improve. So green chemistry is the verb, assessment is the noun. And so that's kind of the way I look at it from a sustainability perspective. Life cycle evaluation, if you look at all the 12 principles of green chemistry and you spread out a life cycle assessment, in my words, going from environment to environment, you can see that if you look at marketing, marketing only touches a few of the 12 principles, but if you look at research and development, you see that it touches all of them. That's what I mean when I say that green chemistry is best fit for an R&D effort. The business issues of green chemistry. Obviously, the Pike research came out with this report recently, and you guys can look at this. I'm sure you're all aware of it, that the prediction is by 2020, green chemistry is a $100 billion market. It is my assumption that every company gets this, wants to do it. They're struggling because their workforce isn't capable of delivering it, but that doesn't mean they don't want it. And so how do you live in a world where you want something, but you can't have it because the training isn't quite up to snuff yet? And so essentially, you know, from a business perspective, obviously it's not enough just to have an environmentally benign alternative. You also have to have something that's going to perform better, and it's going to have to be more economical, or no one's going to buy it. And so you can have the greatest sustainable technology in the world, but if it doesn't work and it's too expensive, no one's going to use it. So if we're really going to make inroads, we need all 3 of these things. We need to have the safety, the performance, and the cost. However, you know, when you really think about this, you know, people oftentimes talk about this 3-legged stool of environment, cost, and performance, and I only use it tongue-in-cheek because I actually don't believe entirely in this picture. What do I mean by that? If you're in business and you're selling a product, all right, I get performance, I get cost. If I talk about the environment, I'm just going to get beat up at the boardroom. I'm going to go, well, how is that going to help the bottom line, blah, blah, blah. It sometimes gets a little nebulous. And I think it's a mistake to actually focus on that as a third tier. When in fact, if you have an educated consumer, if people on this phone call who are dedicated to educating the population about the risks of chemicals in the environment do their job and they start demanding products that are safe, that isn't an environmental issue, it's a performance issue. Okay, so marketing can in fact address this thing. Is, if the consumers want a safe product, that's not an environmental issue, it's a performance issue. And if people working in regulatory worlds are developing regulations to make it more problematic to have a nasty thing, that's not an environmental issue, it's a cost issue. So if we do our jobs right, we don't have to ask for people to be doing this out of altruism. It really ends up being a cost and performance issue, which is the language of business. Okay, and so yes, I personally feel passionate about the environment. We think that it should stand alone. And if, I don't know that we would want a world where I was capable of engineering human thought. It would be a very dangerous, scary world. But, so let's assume that I can't do that. So the next best thing is how do we make this work that is consistent with existing market drivers? And so that's the way I look at how that all fits together. And 5 years ago, Amy Cannon and I, in collaboration with Jim Babcock, we started the Warner-Babcock Institute for Green Chemistry and Beyond Benign, the nonprofit that's doing the education work. Joe Pont is the CEO of the Warner-Babcock Institute. I'm running out of time, so I'm just going to fly through this. A lot of people ask me to give a little bit more information on what the heck is the Warner-Babcock Institute and how does this fit into the grand scheme. The PowerPoint slides will be available, but essentially we're 15 miles north of Boston in Wilmington, Mass. It is a 42,000 square foot research facility to die for. Every piece of scientific research equipment that I've ever needed in my life is all under one roof. Jim Babcock is an amazing person that has enabled this institute to come into existence, and we really touch all aspects of industry. So our core technologies, I won't waste your time, there are 6 things that we do at the Institute that are really kind of unique to us as chemists in way of changing molecules and materials. And we apply these core technologies to 5 different industry sectors. And these are the energy and the environment, chemical sciences, textiles, materials and coatings, pharmaceuticals, agriculture, biotech, cosmetics, personal care, and consumer. And what the Institute does is we have 2 models. One model is we'll work with a company that comes to us and asks us to help them invent a technology. We charge our cost. Okay, and so what they do is they pay our cost. We don't profit. We work for 6 to 9 months to develop the technology at cost. If we succeed and they use it in the marketplace, we want some compensation for that success, be it royalties if it works for them or some other milestone payments. But that's the way we do one thing. And then the second model is we are creating joint ventures and creating independent companies to go and pursue some of our dream research at the same time. So we kind of do a little bit of both. Some examples, people have seen me sometimes with dark hair, sometimes with gray hair. We've invented a non-toxic, environmentally benign hair coloring system. We've invented a non-toxic photoresist cleaning solution. We've got increased bioavailability for neuropharmaceuticals. This is 3 of 25 different examples of things that we're working on. I invite anyone that's interested to look at the website. But this is how I have chosen to manifest green chemistry in the real world. I've decided to give up my full tenured position at a university, chair of the chemistry department, and all this activity and stuff. And I said I put it all at risk because I figured if I could start a company dedicated to the 12 principles of green chemistry and succeed and actually be successful at that, what would be more powerful information as far as green chemistry is concerned? We are in our 5th year in history's worst economy. We've doubled in size every year. We've filed nearly 300 provisional patents, and things are working pretty well, not in spite of green chemistry, because of green chemistry. And I think that's my closing thought, is that people sometimes think that green chemistry is this awful tasting medicine that we have to ram down the throats of industry or whatever. It is not. It is the shot in the arm of innovation, of creativity, and it's not a set of handcuffs. It's a liberating way of being truly more innovative in the research labs. Well, that's my story. I've run out of time. Einstein said it best: problems can't be solved at the same level of awareness that created it. Green chemistry, the work that everyone on this call, I assume, is doing in this place, they're all doing Herculean efforts that are changing the world. Lynn and Clinton are helping communicate this to everyone. I'm so proud to be a part of this and to be able to talk to you. Thanks very much.
Saying thank you, John. That was really a very, very broad and comprehensive, I think, look at a lot of issues going on in green chemistry right now. So we're waiting for questions to pop up here. I wanted to just go back to something that you had mentioned in the course of your presentation, and frankly, it's not something that I ever had thought about or would have ever, expressed in this way, but I have heard people say, and you alluded to the fact that some people think that green chemistry is a replacement for other chemistry, and maybe you want to just amplify on that a little bit, John.
Okay, there's two aspects of that. First is how it fits in with what people are doing in the sustainability world that aren't chemists. And so there's chemicals policy advocates, there is, consumer advocates, there's NGOs that are working on ridding the world of hazardous materials. Their work is critical, and green chemistry in no way replaces that. Okay, I have been brokenhearted time and time again where I end up someone who should be my best collaborator, that we're in the same thing, trying to do the same thing, we end up fighting with each other because they accuse me of somehow trying to change the story. And there's no attempt to do that, in my opinion. We need strong and better chemicals policy, and we need strong and better advocacy across the board, period. Green chemistry is an addition to that process, not a replacement of anything going on in that process. The two of them go hand in hand. Now, as far as chemistry is concerned, again, I would not in my wildest dreams believe that green chemistry is somehow to replace current chemistry. Okay, chemistry is a brilliant science. We have amazing chemists across the world that are constantly doing fantastic things. No one needs change what they're doing in some heretical way. That's not what I'm suggesting at all. Again, just because you've got something that's really going well still doesn't mean it couldn't be improved. All I'm suggesting is that we take a look at how we train the scientists and get more information into their hands. Yes, I know the curriculum is crowded. Yes, I know that their curriculum isn't even available by and large. That's why Beyond Benign is doing what it's doing. So it isn't really a criticism of how we teach chemistry. We're doing amazing things, and I think the field of chemistry has a lot to be proud of. But green chemistry needs to be added, and it's not a one-size-fits-all. One university might want to have a required course for all students. Another university might want to integrate it into many different courses. Another university might want to have it integrated into their labs. There are people working on all the diversity, and we have to have all different approaches. There's no one-size-fits-all. All I ask is that it be not just to the students that are interested, but it be to all students. If you think about it, many professions have licensure. Doctors, lawyers, teachers, nurses, architects all have to have a license and have to renew that license on a periodic basis. In chemistry, we have no such thing. Anyone can make a molecule that has never existed before, and never in their training have they ever had any training how to identify hazard and potential impact on the environment. We need to change that. So it's not to replace the chemistry curriculum, it's to add to it. And I realize it's hard, and that's why Beyond Benign is dedicating a massive amount of work and energy to try to come up with ways that can help each organization try to do this. And you'll hear a lot more about that from Amy next month.
Great. I do now have a bunch of questions which we'll try to get through. Can you give some more details about some of the promising chemistries coming out of Warner-Babcock?
We got a lot of interesting things that are going on. One of the policies that we have is that I will never put the logo of a company that I'm working with on the screen. I feel that it's up to them to be successful without us, and if we can help them for a period of time, that's great. But that's just my feeling. It's not from them requesting it. It's me personally saying I'm not going to list the names of the companies. But we have, one of the issues that we've got is this thing called non-covalent derivatization. In the pharmaceutical industry, there are two huge issues that are around pharmaceuticals and the environment. One is that, obviously, if people are measuring, drinking water in municipalities and increasing amounts of pharmaceuticals are appearing in water supplies, we need to deal with that. And one way to deal with that is to lower the dose that people take. And most people don't realize this, but when you take a prescription drug, you probably, 80 to 90% of it you're excreting out because everyone's different in how they absorb. If we can make more targeted pharmaceuticals, then we can lower the amount of stuff that's going into humans. And obviously, if there's a lower dosage, we're manufacturing a lot less. And so that's one area where we've been working in anti-cancer and antibiotics, in neurological diseases. That's one area. In cosmetics, we have a whole bunch of different applications. We have hair coloring, hair curling, and things like that. In electronics, we have some alternative energy programs. We have some photoresist technologies. And I can go on and on. If anyone wants to look on the website, there's some examples there, but we're trying to, what's beautiful is we focus on molecules, not on the application. We partner with people who understand the applications. We know molecules, hydrogen bonding and pi stacking and stuff like that. We work with people who know their business. We know at the molecular level how to build in sustainability. So we'll take on anything that has a molecule in it.
I think that's we have a great segue into our next question, but before I answer that, somebody asked if there would be an encore presentation, and I just want to remind everybody that this webinar is being recorded and that you will be able to access it hopefully within a week at our website, which is www.glgc.org. It's on your screen right now, or through the Michigan Green Chemistry Clearinghouse, www.migreenchemistry, I think it's .org as well. And in any case, you can see it on your screens right now. So we will not be having an encore, but they will be available. So I'm going to try to rush in some questions. We have several. And building on your golfer analogy, merely changing grip or stance may make you a better golfer, but professional golfers have certain physical attributes like eye-hand coordination or muscular strength, flexibility that just can't be changed on an individual. Isn't that true of chemistry and chemicals, that some are just so good they can't be replaced?
Yes and no. First of all, one disclaimer, I would suggest that no chemist be hired solely because they do green chemistry. In industry, we need excellent world-class scientists that can invent technologies. Green chemistry alone is not an employable field. Someone who does medicinal chemistry at an excellent level, who adds green chemistry, is now world-class. Someone who works in the electronics industry who also knows green chemistry is now world-class. And so doing green chemistry alone will never replace being an excellent chemist in the first place. So that's comment number one. Comment number two, yes. Today, it is inconceivable. There are certain molecules that are out there that have performance that, man, they still have this problem, but, oh, God, are they amazing. And we can never replace them. Well, as a scientist, I never want to believe something is truly impossible. They could be impossible by today's standards and by today's level of understanding. But that doesn't mean 20, 30, 40 years from now that something couldn't happen. And so, yes, there are some, we have to pick and choose what we're going to work on short term, middle term, and long term. And some things are just so difficult to imagine a change that I don't expect to see a change in my lifetime. And anyone working in that industry probably has job security because it's so difficult to replace. But I also refuse to say it can never happen. We can't have anyone in science that says something can never happen. I'm skeptical. We got to be more optimistic about that. It may be very difficult and take decades to do, but that's not the same as saying it can never be done. And so from a business perspective, there are nevers, obviously, because there's a certain box of reality. But yes, there are Herculean molecules that are very difficult to right now conceive of a good replacement. And either legislative action is going to have to change that equation if it's truly nasty, or market forces will have to change that equation if it's truly nasty, or we're just going to have to be patient and realize it's going to take a long time to invent that alternative.
Thank you, John. I have a very long list of questions, and we're basically at the end of our webinar. I'm going to ask you if we can impose on you to send you these questions and have you answer them perhaps in writing so that we could post that on our website. There are so many interesting questions here that I think you would be interested in. So how about I send you the questions and you let me know if you can.
Be happy so. Sure.
Do them. Great. Well, we're at 2:59, everybody. I want to thank John for doing this great webinar for us. I want to thank everybody for joining in on the webinar and remind you that, again, our next webinar is going to be in September with Amy Cannon on September the 12th at 3 p.m. And I encourage you to check out our website for more information and updates about what's happening. And as I said, we will post these answers and questions and answers on the Great Lakes Green Chemistry website, and I suspect on the Michigan Green Chemistry Clearinghouse website as well. Thanks, everybody, and we'll talk to you next time.
Thank you.